Welcome to this webinar. Before we begin the presentation, I want to provide you with a few housekeeping items. On your screen, you will see a taskbar with icons. Each icon is assigned to a particular element of today's webinar. Click on the person icon to learn more about today's speakers. Throughout the presentation, you can network with others or submit questions to the speakers in the Q&A and chat box next to the slides. Download resources from the cloud icon. After the webinar is over, please take our survey to tell us how we did. Today's event is being recorded and archived and will be available within 24 hours. For on-demand questions or comments, send us an email by clicking Need Help? Email us. If you experience any technical issues today, please refresh your browser by hitting F5 for PC or Command R for Mac. And now I'm excited to turn it over to today's moderator.
Good afternoon and welcome to this webinar, Sustained Performance of Thermal Fluid Management. This event, brought to you by Process Heating, is sponsored by Paratherm Heat Transfer Fluids, a Lubrizol company. I'm your moderator, Linda Becker, the Associate Publisher and Editor of Process Heating, and thanks for joining us. Today's speaker is Edward Cass. Ed is the Technology Manager at Paratherm Heat Transfer Fluids. He holds a bachelor's degree in chemistry from Bloomsburg University and has paved a career in specialty chemicals, including heat transfer fluids, synthetic lubricants, functional silicones, reactive silanes, and semiconductor gases. Ed has well-rounded experience in process chemistry, research and development, formulation science, and project management. Don't forget to submit your questions today, and later in the program, Ed will address as many as he can. Today's event is being recorded, and it will be archived on webinars.processheating.com. And now, without any further ado, I'm excited to turn it over to today's presenter, Ed Cass.
Well, thank you for the introduction, Linda, and hello to everybody who's tuned in today, and welcome to Sustaining Performance, Thermal Fluid Management. So what we're focusing on today are the key considerations for maintaining optimal performance from your process-critical thermal fluid heating systems. We're going to talk about why system performance really matters and how fluid selection and maintenance, as well as managing and preventing degradation, are all crucial to sustaining performance. Towards the end of the presentation, we'll discuss some tips and tricks for monitoring performance and keeping everybody on their way. So a quick word about Paratherm. Paratherm was founded in 1988 and later acquired in 2012 by the Lubrizol Corporation. Lubrizol is a wholly owned Berkshire Hathaway company. Established in 1928, Lubrizol is a global leader in specialty additives, advanced materials, and oil field solutions. Paratherm operates under the CPI Fluid Engineering Industrial Products segment of Lubrizol. Modern day, Paratherm offers a range of fluids engineered for closed-loop liquid phase thermal fluid systems for heating, cooling, or both, with operating temperatures from negative 127 degrees Fahrenheit to 675 degrees Fahrenheit. Some key advantages of working with Paratherm. Paratherm products are stocked strategically across the world, and material is always ready to ship. There are essentially no lead times. 24-hour emergency shipping is available, and sales and technical support is also available around the clock. When it comes to quality, compliance, and technical resources, Paratherm is backed by world-class support through the Lubrizol network with extensive test capabilities, highly efficient supply chain, and extensive regulatory knowledge. So let's go ahead and jump right in. Let's ask ourselves, why do we care about sustained performance? And it's simple. Thermal fluid fuels your production process. Your production process fuels your business makes money, and then they pay you. And you really like money. In all seriousness, downtime is expensive, and your processes rely on consistent, responsive performance from your thermal fluid. And that is truly why we care about sustaining performance. So let's talk about how fluid selection impacts sustained performance of your thermal fluid. So some definitions, what the heck are we talking about, Ed? We're talking about heat transfer fluids, also known as thermal oils or thermal fluids, heating and or cooling fluids, hot oils, etc. Often, a thermal fluid may be recognized solely by its brand name, such as Paratherm. The point is, I want everybody to be aware that there are several aliases for heat transfer fluids, and so you may come across one or more of these terms when comparing fluids from different suppliers. For those who are not aware, some characteristics of thermal fluids. Unlike steam systems, thermal fluid systems are capable of generating high temperatures with low system pressures. When properly operated and maintained, thermal fluids offer safety, little ongoing maintenance, and long operating lifetimes. Thermal fluids are highly efficient, non-corrosive, and allow for accurate, uniform temperature regulation in a wide variety of processes. In terms of fluid classifications, there are a plethora of different chemistries available on the market that can be considered heat transfer fluids. By far, water and glycols tend to be the most widely utilized. However, they are limited in their operating range, and that's where a lot of the other chemistries come in. Mineral oil fluids are petroleum-derived and consist of mildly refined API Group 1 oils to highly refined and purified white oils. For the highest temperature liquid phase service, synthetic aromatic fluids are used. As far as this presentation is concerned, we are focusing on non-aqueous, natural, and synthetic hydrocarbon-based heat transfer fluids in closed-loop systems. So essentially what we're focusing on is anything that falls within the mineral oil and synthetic chemistry areas in the figure shown. So first and foremost, selecting the proper fluid. The most important aspect of sustaining performance is using the proper fluid matched to your application. There are several selection criteria to focus on when making the right choice for your thermal fluid system. The questions for consideration are, what are the minimum and maximum operating temperatures going to be? What is the lowest startup temperature that could be experienced given the climate and environment? What is the fluid purity? Lower purity fluids may have higher fouling potential. Is there any benefit to using a fluid with specialized additives in your application? Something to note is that additives may narrow the operating range of the fluid. Is there any preference for a synthetic fluid versus a mineral oil? Are there any considerations to be made with existing fluid chemistry or any handling and disposal concerns at the plant level? And then there are process considerations which may also affect the fluid choice. Is this an existing system? If so, then fluid compatibility must be taken into consideration. You don't want to mix fluids that might not be 100% miscible in the system. Is this a continuous process or a batch process? Continuous operation means that accelerated degradation of the fluid may occur. Again, we have to consider the local climate. What are the environmental maxima and minima? Is the system vented to the atmosphere? If yes, then oxidation potential should be minimized, and consideration of vapor odor should be taken as well. Does the system require heating and cooling capability from the fluid? Keep in mind, certain fluids are advantageously engineered specifically for heating and cooling purposes. In terms of performance considerations, heat transfer fluids that are engineered for sustained performance will maintain a balance of purity, stability, and efficiency. In addition, some ancillary features to consider might include the thermal expansion rate, the flash or fire point of the fluid's inherent resistance to oxidation, the vapor pressure of the fluid over the operating range, and the cost of the fluid versus the anticipated performance of the fluid. So, when it comes to making the right choice, it comes down to the age-old saying, don't put a square peg in a round hole. The ideal product for a given application will, Meet the minimum and maximum temperature requirements with cushion. In general, you don't want to select a fluid with a maximum operating temperature that's equal to the average bulk operating temperature. There may be some exclusions for high temperature liquid phase service where options can get limited at very high temperatures. But in general, having some cushion there will help minimize degradation of the fluid. The ideal product will be compatible with all system components as well as the operating environment. If you're in northern Montana, for instance, you may need to consider how the local climate could affect your startup conditions. The ideal product will provide a reasonable lifetime given the process conditions. Keep in mind that lifetime of the fluid is highly dependent on many process and system variables. In general, it's always a good idea to contact your fluid supplier for assistance in selecting the most appropriate product. Your fluid supplier will help make sure that you are getting the level of performance you need from your fluid. So with proper fluid selection behind us, let's go ahead and switch gears and discuss fluid degradation. So you might be asking yourself, why do we even care about fluid degradation, Ed? Because fluid degradation either reduces the safety margin or increases the amount of maintenance required of the system or the fluid. We need to acknowledge that fluid degradation over time is normal and inevitable. However, the goal is to minimize the rate at which it occurs. So what happens to the fluid? Well, demanding process conditions put excessive stress on the fluid and cause it to break down. After several thousand miles, your engine oil loses its effectiveness to properly perform its job, and so you take it to the local Jiffy Lube to keep it purring nicely. Thermal fluids are very similar in this regard. Over time, fluid properties and composition can deviate outside of established optimal ranges due to external stresses, reducing the fluid's ability to properly perform and ultimately threatening process requirements. In general, there are three possible degradation pathways for the fluid. There's thermal degradation, there's oxidative degradation, and then there's contamination. There's also potential for any combination thereof. Let's talk about thermal degradation. Thermal degradation is caused by excessive thermal stress on the fluid due to low velocity, burner misalignment or malfunction, improper startup or shutdown procedures, and/or coking of the heater tube or the heater elements. The effects of thermal degradation are serious: permanent damage to the chemical structure of the fluid and subsequent changes in physical and chemical properties, such as viscosity, density, flash point, heat capacity, or thermal conductivity. Thermal degradation impacts coking potential, proper pump operation, total system efficiency, and also operational safety. How do we identify thermal degradation? The fluid may smell like gasoline or diesel. Distillation analysis may indicate that there's some deviation from the baseline values in terms of low or high boilers. Significant changes in viscosity may also occur, either low or high. Let's talk about oxidative degradation. Oxidative degradation is a result of hot fluid reacting with atmospheric oxygen in vented expansion tanks and reservoirs. The effects of oxidation are typically an increase in total acid number, which can lead to sludge, varnish, or coking, increased viscosity, or also the possibility for corrosion of system components. Oxidation impacts may include plugged lines, pressure drops, reduced flow rates, fouling of heat exchange surfaces, cold spots, and reduced heat to the process. How do we identify oxidation, Ed? Good question. We look for increases in acidity in the total acid number. Fluid thickening is a good indication of oxidation. Increase in solids is a good indication of oxidation. And a foul odor or even a darkening of the fluid can indicate that there's oxidation occurring. Contamination is typically caused by process leaks, moisture ingress, or operational error, such as adding the wrong fluid to the system, sharing process equipment such as pumps or lines, or inadequate cleanout procedures. In general, contamination affects fluid quality and/or critical fluid properties. Contamination can lead to vapor eruptions from the expansion tank, fouling of heat exchange surfaces, and/or proper pump operation. The impact of contamination: operational safety, reduced process flows, reduced heat to the process, or even equipment failure. How do we identify contamination? An increase in total acid number, solids, and/or viscosity is a good indication that there could be contamination. Deviation in the boiling range is a good indication. Atypical odor or color is a good indication. And high moisture content is definitely a good indication. Sometimes you can even see water separating if you take a sample from the system. You might even be able to see water separating from the bulk oil phase. Contamination is not necessarily identified by any one of these things, but a combination of the analysis to help prove that there is contamination. In the spirit of discussing fluid degradation, let's take a quick look at fluid appearance. Color is something that customers often question. They say, hey, my fluid is black, it must be bad. In reality, in-service fluid may naturally darken over time. This is especially true for systems that are vented to atmosphere. Color is a very basic indicator of fluid degradation. As I mentioned, most fluids that have been in service for more than 1 year will be yellow to amber in color. Often, fluid may look black, but when shaken and observed under a light source, most fluids will show that they are actually a dark amber in color rather than black. Fluid that is truly black is most likely heavily oxidized or degraded. The simple visual analysis provides a quick way for anyone to assess the general health of their heat transfer fluid. Safely take a sample from the system into a glass jar. Allow it to sit and equilibrate for a short time. Slowly invert the sample under a light source and note, is there any level of sediment in the bottom of the jar? Then shake the jar vigorously and observe how long it takes for the film to clear up on the side of the jar. High levels of sediment or long time to clear indicate that there could be heavy suspended solids or heavy sediment moving through the pipes of your system. So let's review some of the signs that there might be a fluid-related issue going on. Some common fluid-related symptoms: line blockages and/or pressure drops, decreased flow, cold spots, pump cavitation, insufficient heat to process, expansion tank eruptions. Note that these symptoms do not guarantee a fluid-related problem, but they are indicative that there could be a fluid-related issue. Sending a fluid sample for analysis is a quick and effective way to rule out whether or not you have a fluid-related system issue. So let's talk about the importance of fluid maintenance on sustained performance. Condition monitoring of your thermal fluid is critical for sustaining performance. As we've discussed already, changes in fluid quality can impact the ability of the system to meet anticipated demands and can lead to unplanned downtime. Routine analysis alerts the end user to both the fluid condition and also can help detect equipment issues or malfunctions before they become catastrophic. And so the end result is proactive versus reactive maintenance. And when you're proactively maintaining the system, you're most likely going to get maximum performance from the system and reduced operating costs overall. In other words, you'll be smooth sailing. So a quick primer on fluid analysis. When should you analyze your fluid? New systems should be sampled within the first year of operation and annually thereafter. Existing systems should be sampled within the first month of startup and annually thereafter. And any time a possible fluid-related symptom is observed is a good time to sample. What should you analyze? You should ensure that the fluid testing is specific to heat transfer fluids. Acid number, viscosity, carbon and solids loading, and distillation range, and/or flash point are considered standard tests in the industry. The analysis report should include proposed causes for deviation from baseline values, and corrective actions should be recommended. In terms of how to take a fluid sample, for high temperature systems, ideally the fluid sample is taken hot, around 180 degrees Fahrenheit or so, with the pumps running from an active part of the system. Somewhere around the pump suction is usually a good place to take a sample. Some systems may be fitted with a true sample port for this purpose. Purge some material from the sample port to clear it out. Take your sample directly into the container that will be sent to the lab. In other words, don't take a sample into one container and then transfer it into another. Doing so could give incorrect recommendation. It's important to note that safe sampling practices should always be observed with high temperature heat transfer systems. Samples from the expansion tank may not be representative and should be avoided. So let's discuss in more detail the critical test for determining the health of your heat transfer fluid. Total acid number is run by ASTM D664. Acid number measures the level of organic acids in hydrocarbons via potentiometric titration. The meaning of the acid number test is that it is indicative of the degree of oxidation the fluid has undergone and/or can indicate potential contamination. The lower action limit can be 0.2. We can see carbon levels being generated with acid numbers as low as 0.2. Proactive maintenance may suggest partial replacement depending on the level of carbon loading. In terms of the upper action limit, acid numbers in excess of 0.4 are generally associated with heavier carbon levels and may warrant partial or full replacement depending on the carbon loading. I should note that carbon can also be managed with filtration. For systems that do not have filtration, these action limits may be more important. Kinematic viscosity is measured by ASTM D445. Viscosity is a measure of the fluid's thickness or resistance to flow as a result of internal friction. Viscosity increase is indicative of oxidation and/or can indicate potential contamination. Viscosity decreases are generally indicative of overheating. In general, the lower action limit is plus or minus a 35% change in viscosity and indicates the molecular structure is compromised. Proactive maintenance might suggest a partial replacement with levels around 35%. Deviation in excess of 50% from the original baseline value indicates significant molecular changes to the fluid. At this point, replacement is generally warranted. Distillation range is assessed by ASTM D2887. We use gas chromatography to separate all components in the fluid by their boiling point. Recall that heat transfer fluids are often a mixture of different components, and so they have wide boiling ranges, and that's what this test helps us see. An increase in lower high boilers relative to the new fluid baseline indicates that there are changes in the molecular structure as a direct result of fluid degradation and/or potential contamination. If low boilers are elevated, it is indicative of overheating, thermal stress on the fluid. If the high boilers are elevated, it is also indicative of overheating, oxidation, and/or contamination. In general, low boilers or high boilers in excess of 9% may suggest a partial replacement of the fluid to help restore optimal properties. Low or high boilers in excess of 12% might suggest that a full replacement of the fluid is necessary in order to maintain optimal properties of the fluid and optimal process requirements. So you've noticed a decrease in performance, and your fluid analysis came rated in poor condition. Time to replace, but is there anything else you should do? A fluid changeout alone may not restore performance to optimal levels. In that case, you may consider system cleaners. Cleaners should be considered if degradation byproducts have been detected and performance has dwindled. There are two basic types of system cleaners. First, there are solvent-type cleaners that are typically used at 100% concentration and help to chemically dissolve degradation byproducts. Alternatively, on-the-fly additive-type cleaners work by replacing a small volume of the system fluid with the additive cleaner. The cleaner is run under normal operating conditions. It works over the course of a few weeks and is later discharged, and the system is refilled when convenient for the plant. Whether you're cleaning or not, waste oil and/or cleaner should always be responsibly recycled or disposed of per local regulations. Now that we've discussed the different kinds of degradation that can happen, and also how we can detect that degradation with laboratory analysis, the question remains, what can you do to prevent fluid degradation? In terms of preventing fluid oxidation, ideally, you can put an inert gas blanket on the expansion tank, such as nitrogen. This eliminates oxidation altogether so long as the system is working properly. If that's not an option, there are some other things you can do. It's good to ensure that the expansion tank and expansion line are not insulated. It's good to maintain the expansion tank temperature at less than 150 degrees Fahrenheit in vented systems. This helps lower the activation energy for oxidation. It's a good idea to run the expansion tank at 66 to 75% capacity while at operating temperature. Running at higher volume in the expansion tank helps to dissipate heat across the surface of the tank. It's a good idea to ensure that the expansion line closest to the pump is the only line open to the tank. In double drop leg expansion tanks, that means that the line closest should be open, and the warm-up valve, the line that's further away from the pump, should be closed during normal operation. You can also consider the installation of a cold seal pot, which will help prevent the tank from breathing in air as the fluid goes through thermal cycling. Preventing overheating. Maintain proper flow through the heater at all times. Ensure that your pump is adequately sized for the design flow rate and also maintains adequate velocity through the heater. 8 to 10 feet per second is generally considered good, sufficient velocity. Avoid operating at or above the maximum recommended operating temperature. The closer you operate to the maximum recommended operating temperature, the more rapidly the fluid will degrade. Perform routine preventative maintenance on system components. Check with your heater manufacturer and other system component manufacturers to ensure that you're on the proper schedule. And you should always follow proper startup and shutdown procedures. Failure to do so can result in accelerated fluid degradation. In terms of preventing contamination, protect the system against moisture ingress. Avoid hydro-testing the system if possible. Only add fluid to the system that is explicitly designed for high-temperature heat transfer service. And use dedicated equipment, such as your pumps and hoses, when charging or topping off the system so as to prevent contamination from other residual fluids in those pieces of equipment. So, in terms of general performance monitoring, the best thing you can do is routinely walk your system and pay attention to the sights and sounds. It can be helpful to keep a log on system pressures, temperatures, and any abnormalities noted. Reviewing fluid and process performance. Ensure that you have stable heat supply and stable energy usage. Any jumpiness in these measures are indicative of a process problem. From a process perspective, keep tabs on your cycle times, your system pressures, and the time it takes for startup and shutdown. In terms of equipment monitoring, your heat source. Ensure proper velocity and flow rate through the heater. Monitor your film temperature, stack temperature, and average fuel usage if possible. Follow the manufacturer's preventative maintenance schedule to ensure proper burner operation and alignment and general performance of the heater. For pumps, ensure that your pumps are properly installed and aligned to minimize vibration. Take action on any leaks immediately. Ensure flow and pressures are stable. For other equipment, monitor pipe condition, flange connections, insulation, and the inert gas system. Make sure everything looks good. Any leaks that are noted should be addressed as soon as possible for safe and efficient operation of the system. Lastly, I wanted to provide some quick tips that we may or may not have already covered in the previous slides. For system charging, again, make sure you've got the proper fluid. That is first and foremost. Avoid filling the system from the top down, but rather charge from low points to displace air in the system. Open all your high point vents to help displace air. Avoid mixing fluids when possible. For removing water, ensure that you're raising the temperature slowly to avoid flashing steam. Allow moisture to vent from the expansion tank and monitor collection so you can be sure that you're getting it out. Ensure that the warm-up valve is closed after the boil-off procedure is finished. As we talked in the thermal degradation slide, or the oxidation slide rather, you want to ensure that that warm-up valve is closed so that you can help sufficiently cool the fluid before it hits the expansion tank. In terms of preventing rapid degradation, do not exceed the maximum operating temperature. Monitor your flow rates and pressures. Never operate with the warm-up valve in the open position. Establish and execute proper startup and shutdown procedures. And be sure to perform routine fluid analysis. I can't stress that enough. For fluid storage, store drums and totes indoors if possible. Drums that are stored outdoors should be stored on their sides if possible to help prevent moisture accumulation on the tops. Tank storage should ideally be padded with nitrogen and otherwise free of environmental contaminants. Utilize pressure gauges at the heater inlet and outlet, the pump inlet and discharge, before and after heat users, etc. Utilize PLCs and DCS controls for improved automation. Consider side stream filtration to help keep the system clean. Again, if you have accumulated carbon in the system from oxidation, filtration can be an effective way to keep the carbon levels under control, even if the total acid number is increasing. However, it should not continue to increase indefinitely because you can still have other issues such as corrosion. In terms of startup and shutdown, try to keep the heater should remain in low fire until turbulent flow is reached or proven. On shutdown, the main pump should be kept running until the bulk temperature of the fluid drops below 200 degrees Fahrenheit. And with that, we're all wrapped up. I want to thank everybody for tuning in and left a lot of time here for questions and everything. So I will go ahead and turn it back over to Linda.
Well, thank you, Ed, for a great presentation. Why don't we go ahead and jump right into the questions? I saw that we had a few. The first one is, where in the system is the best place to take a sample?
So in most systems, the best place to take a sample is somewhere around the pump suction. It really depends on the system design and how it's set up, if it's a large system or a small system. But in general, for medium to larger size systems, somewhere around the pump suction is ideal. This is a low pressure point, and there's usually a tap there of some sort to be able to go ahead and take a good representative sample.
All right. Well, here, next question is, what if I cannot take my sample while the system is hot?
And that's okay if you can't take a sample while the system is hot. Taking a hot sample is ideal for higher temperature systems. It helps ensure that the fluid is in turbulent flow and that we're getting a good representative picture of everything that's moving through the pipes, whether it's small particulates, carbon, metal that might be moving around in there, etc. So that's why we try to recommend taking the sample hot. But if you can't, that's okay. In terms of the basic properties of the fluid that we analyze to check up on the fluid health, we can still perform those tests, and so that's okay. But it does help a little bit if you can get it hot, make sure the fluid's in turbulent flow, and make sure that we're getting a good representative picture. So, but we can still make good recommendations for any corrective actions on the fluid if necessary.
All right. I'll read this one sort of slowly. It's sort of a longer question, so I don't want to go off script here, so to speak. It says, normally the condemnation limit for TAN in sensitive hydraulic systems is 1. Why is the TAN condemnation limit for thermal oils so low? I've seen systems with a TAN of 3, and the oil marketing company says that it was within limits. Can you comment on this?
Yeah, that's a really good question, and I probably should have inserted a disclaimer. So acid number is the action limits for a lot of the tests that are run may vary from fluid manufacturer to manufacturer. For us, what I've done is I've provided our typical limits. But that being said, the low acid threshold is really because we've seen carbon buildup occurring with relatively low acid numbers. So ideally, we want to keep it low so that we're not generating carbon. I did mention that if you do begin to accumulate carbon in the system, it can easily be managed with an offline or side stream filtration system, which will help keep the solids down. It'll help keep carbon from agglomerating and sludging up in the system. And that's really the ultimate goal. So we set those limits low because we've seen that, a lot of systems are not set up well for getting the carbon out of the system. Maybe they're smaller systems and it's hard to pipe something like that in. It's not practical. They don't want to do it. Whatever the case. So we keep it low, and again, they're just recommendations. But that's really the reason. We just want to prevent accumulation of carbon in the system, and we do see carbon begin to generate and even accumulate with fairly low acid numbers. And another note is that different manufacturers also have different initial total acid numbers. Most of our fluids are very low, around 0.01, but some fluids, when they're brand new, can have acid numbers of 0.2, 0.3, 0.4. So it's somewhat fluid specific and supplier specific. That is a good question. And in general, the condemnation limit is around 1.0. Regardless, that's a good place to just say, hey, it's time to change.
So that would be a condemnation limit for, because the same questioner asked, what would be a condemnation limit for flashpoint for thermal oil?
So typically, I think changes of 50% would be a condemnation level. Changes of less than that, maybe 35% or so, could be cause for concern. Definitely a cause for, investigating, why has the flashpoint changed so much? It's important to take all of these things into consideration as a whole. We can't just look at flashpoint or acid number or viscosity, by themselves and say that, there's hard and fast rules. So the analysis typically includes a series of tests to get a general picture of the overall health of the fluid, and that's really what we want to do. But for flashpoint, yeah, 50% I think would be a condemnation limit, and levels, changes of 35% or so would be cause for concern. And again, that may also depend on plant personnel, safety personnel at the plant level, or any other policies that might be in place at the plant level for what's tolerable and what's not.
All right. Is it safe to use a heat transfer fluid above its flash point?
Yes, it is common for heat transfer fluids to be operated above their flash point. Very common in basically any high temperature heat transfer system. In order for a flash to occur, you've got to have the entirety of the fire triangle. You've got to have the fuel, you've got to have the oxygen, and you've got to have an ignition source. In heat transfer systems, they're closed loop systems, so you never really have appreciable vapor pressure with an ignition source and also sufficient oxygen to sustain any type of fire. I did try to emphasize that fluid leaks are important, right? Because that's a little bit different. If you have fluid leaks at points of the system where you have hot fluid and you have oxygen, if there's drips on an ignition source or potential ignition source, that could create a dangerous situation. And that's why leaks should be addressed immediately. In most cases, if there are leaks, they're usually pretty small. And what happens is the fluid more or less tends to oxidize upon contact with the atmospheric air around it, which changes the composition, and it also immediately cools the fluid, and so the potential for ignition drops significantly.
All right. And is there any general rule of thumb for how often you should change your fluid?
Yeah, fluid lifetime is just so dependent on system variables, many different system variables, and there's no tried and true rules of thumb for that. We recommend getting fluid analyzed at least once a year, and that way you can keep tabs on the health of the fluid. We can make recommendations on whether or not any changes should occur, any fluid replacements necessary, or whether any particular system components or parts of the process should be reviewed, to help prolong the lifetime of the fluid. So, again, no hard and fast rules. The limits on the analysis are a good starting place to determine whether or not you need to make any changes. But if the tips that were presented herein are followed, that's how you can maximize performance and get the best lifetime out of the fluid.
All right. One question that I had is, can you talk a little bit more about side stream filtration and its role in basically extending the life of a heat transfer fluid?
Sure. So the side stream filtration units are just that, right? They're generally piped off of the main supply lines. A small portion of the process flow is directed through the side stream filtration, and over time it can help to reduce any accumulated solids or carbon or anything like that. The filtration units are generally designed to have smaller tolerances than what a typical Y strainer screen would do, right? So Y strainer screens are generally in place just to help protect the pump from any significantly large solids, but they're generally, a larger mesh size. Side stream filtration units tend to be smaller micron thresholds and help to remove some of the smaller contaminants from the system, and that helps to keep accumulated carbon from, again, agglomerating and creating more issues in the system. So it's important to ensure that if you are planning on installing a unit like this, that all of the components that are going into it are rated for the temperatures and or pressures that might be seen in that particular loop where it's going. You don't want to be melting plastic or anything like that. So the filter housing and the filter elements and all of that should be rated for the pressures and temperatures that the system is seeing.
Okay. What test do you recommend for testing carbon loading?
So carbon loading can be generally assessed. Actually, if I go back to this slide here, you can generally assess the carbon loading of the fluid visually. That's a good way to do it if it's significant. And you can see, looking at the base of the jar that's inverted up in the air, if you have some of that accumulated sediment like that, it's obvious that you've got some accumulated carbon in the system. The heavier that gets, the more indicative it is that you've got significant sediment either settling out in the expansion tank as it makes its way up there, or even just agglomerating and starting to settle in the piping and low velocity areas. So that's a visual analysis. Some other things you could do, you can do homegrown filtration just through general filter paper, and you can see how much solid content is left behind. And then there's also a test called pentane insolubles that's commonly used in the industry and typically measures insolubles on a weight % basis.
All right. Are there any concerns about activated carbon filtering?
Concerns? I don't hear about people using activated carbon. I'm assuming this means like an activated carbon cartridge. I'm assuming that's what this means, or over carbon, like a packed carbon filter of some sort. Again, I think it's just make sure that the components are rated for the temperatures. Carbon is often used for removing low-level impurities. It's especially used in purifying drinking water. In terms of process chemistry, it's often used to improve the color of fluids and things like that. It's really not. I wouldn't say it's necessary for thermal fluid systems to use activated carbon filter media in any way. I'm not saying it's not out there and that you couldn't use it, but I have not heard much about people doing that. I think it's more so the wound glass fibers and or even the metal mesh type filter elements that are most commonly used.
Okay, just wanted to throw out to the attendees, we have just a few more minutes for questions, so if you want to go ahead and get those into the chat console, we still have a few minutes, we can take a few more. I did have one follow-up question on the side stream filtration for you, Ed.
Sure.
Is there a regular guideline, or can you give some sort of sense of what would having a side stream filtration system on a heat transfer loop, a closed loop, how much can you really see that extend the life of the fluid?
So it's an interesting question because the carbon loading, unless your contaminants are directly catalyzing degradation of the fluid, right? So if you have like copper chips or something like that, reactive metals or something that are floating around in the fluid at high temperatures, they could potentially catalyze degradation of the fluid in an unwanted way, and then in that case, that could affect fluid lifetime. Oxidation byproducts like carbon, they don't necessarily directly impact the lifetime of the fluid, but if they're left unchecked, that carbon can accumulate in the system and then create bigger problems. You can get carbon that wedges itself into sensor lines, plugs up your pressure gauge taps or things like that, and you can start to get erroneous readings. And then the ultimate is when you get blocked lines, and I'll pull this slide up here that shows, when you get this really heavy accumulation, and that the fluid has just gotten so sludged up that your flows drop and you get line blockages, and you can actually insulate the pipes and reduce the heat to the process. So there's no hard rules here. Keeping the fluid clean is a good goal, and so side stream filtration definitely helps with that, and it helps prevent the situation where you have significant accumulation of of degradation byproducts in the system. The acid number will, generally if you have heavy carbon levels, assuming it's not from contamination, but from oxidation, the acid number is going to continue to stay high. In some ways, even if you're filtering, that acid number may stay high. It may go down if more carbon continues to form from those acids. And it might also continue to go up if the fluid continues to oxidize. So again, it's, the filtration can help protect the fluid, but filtration is more about protecting the system components and making sure that everything continues to hum along nicely, rather than protecting the fluid itself.
Okay, good point. This might be a controversial question. I don't know. I didn't see it mentioned in your presentation, but I might have missed it. What about like the flushing fluids and the system cleaners that you see recommended?
Yeah, they're out there. And cleaners. Cleaners, I did mention a couple notes on the cleaners. You have the concentrated type cleaners, and then you've got the additive type cleaners. Flushing fluids are often used if you're switching fluid types, for instance, if you're switching from a mineral oil to a synthetic or vice versa, and you want to make sure that you've got, little residual of the old stuff in there. But if you've got heavy carbon buildup or any other type of contamination or things in the system, a cleaner is probably more so what you need. But you can always put a flushing fluid through there, which is generally a cheaper, it's a cheaper sort of disposable fluid that you can run just to kind of help flush things out. So they're out there, they're used, but in our experience, they're not really as necessary as an active cleaner is for actually cleaning up degradation products scattered throughout the system. And so I didn't make any note of them in the presentation, but it's a good question because they are out there and they are being used.
All right. Well, it looks like that's all the questions that we have right now live in the console. So with that, I think we're going to go ahead and wrap it up. And I want to ask everyone that's attended to please join me in thanking Ed Katz for his great presentation, as well as our sponsor, Paratherm Heat Transfer Fluids, a Lubrizol company. If you have any additional questions or comments, you can click on the email button and it will send it directly to us, or you can always reach out to me afterwards via the webinar. My email address is on the website. As you exit today's webinar, please take a couple of minutes and complete our survey. We welcome your detailed comments. You can visit webinars.processheating.com for the archive of this event, as well as information about other upcoming events that Process Heating is hosting. We appreciate your time, and we hope that you found this webinar to be a valuable experience. And have a great day.